Last time we attempted to visualize a four-dimensional spatial figure by reducing it to 3 dimensions. First, we converted a 3-dimensional figure into a 2-dimensional one. We substituted colors for dimensions, constructing our image using 3 colors to represent the 3 dimensions of a cube. Then we unfolded the cube so that all of its surfaces lay in a plane, resulting in 6 squares whose differently colored edges represented the 3 dimensions in 2-dimensional space. We then envisioned transferring each square of the cube's surface into the 3rd dimension as moving the square through a colored fog and allowing it to reappear on the other side. We imagined all the surface squares moving through and being tinted by transition squares. Thus we used colors to attempt to picture a 3-dimensional cube in 2 dimensions. To represent squares in 1 dimension, we used 2 different colors for their edge pairs. To represent a cube in 2 dimensions, we used 3 colors. Depicting a 4-dimensional figure in 3-dimensional space required a 4th color. Then we imagined a cube with 3 different surface colors as analogous to our square with 2 different edge colors. Each such cube moved through a cube of the 4th color. That is, it disappeared into the 4th dimension or color. In accordance with Hinton's analogy, we made each boundary cube move through the new 4th color and reappear on the other side in its own original color. Now, I would like to give you another analogy. We will begin once again by reducing 3 dimensions to 2 in preparation for reducing 4 dimensions to 3. We must envision constructing our cube out of its 6 square sides, but instead of leaving all 6 squares attached when we spread them out, we will arrange them differently, as shown here, see figure 31. As you see, we have split the cube into 2 groups of 3 squares each. Both groups lie in the same plane. We must understand the location of each group when we reassemble the cube. To complete the cube, I must place one group above the other so that square 6 lies over square 5. Once square 5 is in position, I must fold squares 1 and 2 upward, while squares 3 and 4 must be folded downward, see figure 32. The corresponding pairs of line segments, that is, the ones of the same color, here with the same number and weight of slashes as shown in figure 31, will then coincide. These lines that are spread out in 2-dimensional space coincide when we make the transition to 3-dimensional space. A square consists of 4 edges, a cube of 6 squares, and a 4-dimensional figure of 8 cubes. Hinton calls this 4-dimensional figure a tesseract. Our task is not simply to put these 8 cubes together into a single cube, but to do so by making each one pass through the 4th dimension. When I do to a tesseract what I just did to a cube, I must observe the same law. We must use the analogy of the relationship of a 3-dimensional figure to its 2-dimensional counterpart to discover the relationship of a 4-dimensional figure to its 3-dimensional counterpart. In the case of an unfolded cube, I have 2 groups of 3 squares. Similarly, unfolding a 4-dimensional tesseract in 3-dimensional space results in 2 groups of 4 cubes, which look like this. See figure 33. This 8-cube method is very ingenious. We must handle these 4 cubes in 3-dimensional space exactly as we handled the squares in 2-dimensional space. Look closely at what I have done here. Unfolding a cube so that it lies flat in 2-dimensional space results in a grouping of 6 squares. Performing the corresponding operation on a tesseract results in a system of 8 cubes, see figure 34. We have transferred our reflections on 3-dimensional space to 4-dimensional space. folding up the squares and making their edges coincide in three-dimensional space, corresponds to folding up the cubes and making their surfaces coincide in four-dimensional space. Laying the cube flat in two-dimensional space resulted in corresponding lines that coincided when we reconstructed the cube. Something similar happens to the surfaces of individual cubes in the tesseract. Laying out a tesseract in three-dimensional space results in corresponding surfaces that will later coincide. Thus, in a tesseract, the upper horizontal surface of a cube 1 lies in the same plane as the front surface of cube 5 when we move into the fourth dimension. Similarly, the right surface of cube 1 coincides with the front surface of cube 4. The left square in cube 1 coincides with the front square in cube 3. And the lower square in cube 1 coincides with the front square in cube 6. Similar correspondences exist between the remaining surfaces. When the operation is completed, the cube that remains is cube 7, the interior cube that was surrounded by the other 6. As you see, we are concerned once more with finding analogies between the third and fourth dimensions. As we saw in one of the illustrations from the last lecture, see figure 49, just as a fifth square, surrounded by 4 others, remains invisible to any being who can see only in 2 dimensions, the same applies to the 7th cube in this instance. It remains hidden from 3-dimensional vision. In a tesseract, this 7th cube corresponds to an 8th cube, its counterpart in the 4th dimension. All of these analogies serve to prepare us for the 4th dimension, since nothing in our ordinary view of space forces us to add other dimensions to the 3 familiar ones. Following Hinton's example, we might also use colors here and think of cubes put together so that the corresponding colors coincide. Other than through such analogies, it is almost impossible to give any guidance in how to conceive of a 4-dimensional figure. I would now like to talk about another way of representing 4-dimensional bodies in 3-dimensional space that may make it easier for you to understand what is actually at issue. Here we have an octahedron, which has 8 triangular surfaces that meet in obtuse angles, see figure 35. Please imagine this figure, and then follow this train of thought with me. You see, these edges are where 2 surfaces intersect. 2 intersect at AB, for example, and 2 at EB. The only difference between an octahedron and a cube is the angle at which the surfaces intersect. Whenever surfaces intersect at right angles, as they do in a cube, the figure that is formed must be a cube. But when they intersect at an obtuse angle, as they do here, an octahedron is formed. By making the surfaces intersect at different angles, we construct different geometric figures. Next, envision a different way of making the surfaces of an octahedron intersect. Picture that one of these surfaces here, such as AEB, is extended on all sides, and that the lower surface, BCF, and the surfaces ADF and EDC at the back of the figure are similarly extended. These extended surfaces must also intersect. There is a twofold symmetry at this line of reflection, also called, quote, half-turn symmetry, close quote. When these surfaces are extended, the other 4 original surfaces of the octahedron, ABF, EBC, EAD, and DCF, are eliminated. Out of 8 original surfaces, 4 remain, and these 4 form a tetrahedron, which also can be called half an octahedron because it causes half of the surfaces of the octahedron to intersect. It is not half an octahedron in the sense of cutting the octahedron in half in the middle. When the other 4 surfaces of the octahedron are Extended until they intersect, they also form a tetrahedron. The original octahedron is the intersection of these two tetrahedrons. In stereometry, or geometric crystallography, what is called half a figure is the result of having the number of surfaces rather than of dividing the original figure in two. This is very easy to visualize in the case of an octahedron. If you imagine a cube halved in the same way, by making one surface intersect with another surface, you will always get a cube. Half of a cube is always another cube. There is an important conclusion to be drawn from this phenomenon, but first I would like to use another example. Here we have a rhombic dodecahedron, figure 37. As you see, its surfaces meet at specific angles. Here we also have a system of 4 wires, I will call them axial wires, that run in different directions. That is, they are diagonals connecting specific opposite corners of the rhombic dodecahedron. These wires represent the system of axes in the rhombic dodecahedron, similar to the system of axes you can imagine in a cube. In a system of 3 perpendicular axes, a cube results when stoppage occurs in each of these axes, producing intersecting surfaces. Causing the axes to intersect at different angles results in different geometric solids. The axes of a rhombic dodecahedron, for example, intersect at angles that are not right angles. Having a cube results in a cube. This is true only of a cube. When the number of surfaces in a rhombic dodecahedron is halved, a totally different geometrical figure results. Now let's consider how an octahedron relates to a tetrahedron. Let me show you what I mean. The relationship is clearly apparent if we gradually transform a tetrahedron into an octahedron. For this purpose, let's take a tetrahedron and cut off its vertices, as shown here, see figure 38. We continue to cut off larger portions until the cut surfaces meet on the edges of the tetrahedron. The form that remains is an octahedron. By cutting off the vertices at the appropriate angle, we have transformed a spatial figure, bounded by 4 planes, into an 8-sided figure. What I have just done to a tetrahedron cannot be done to a cube. A cube is unique in that it is the counterpart of 3-dimensional space. Imagine that all the space in the universe is structured by 3 axes that are perpendicular to each other. Inserting planes perpendicular to these 3 axes always produces a cube, see figure 39. Thus, whenever we use the term cube to mean a theoretical cube rather than a specific one, we are talking about the cube as the counterpart of 3-dimensional space. Just as the tetrahedron can be shown to be the counterpart of an octahedron by extending half of the octahedron's sides until they intersect, an individual cube is also the counterpart of all of space. If you imagine all of space as positive, the cube is negative. The cube is the polar opposite of space in its entirety. The physical cube is the geometric figure that actually corresponds to all of space. Suppose that instead of a 3-dimensional space, bounded by 2-dimensional planes, we have a space bounded by 6 spheres, which are 3-dimensional figures. I start by defining a 2-dimensional space with 4 intersecting circles, that is, 2-dimensional figures. Now imagine these circles growing bigger and bigger. That is, the radius grows ever longer, and the midpoint becomes increasingly distant. With time, the circles will be transformed into straight lines. See figure 40. Then, instead of 4 circles, we have 4 intersecting straight lines and a square. Now, instead of circles, imagine 6 spheres, forming a mulberry-like shape, figure 41. Picture the spheres growing ever larger, just as the circles did. Ultimately, these spheres will become the planes defining a cube, just as the circles became the lines defining a square. This cube is the result of 6 spheres that have become flat. The cube, therefore, is only a special instance of the intersection of 6 spheres, just as the square is simply a special instance of 4 intersecting circles. When you clearly realize that these 6 spheres flattening into planes correspond to the squares we used earlier to define a cube, that is, when you visualize a spherical figure being transformed into a flat one, the result is the simplest possible 3-dimensional figure. A cube can be imagined as the result of flattened 6 intersecting spheres. We can say that a point on a circle must pass through the 2nd dimension to get to another point on the circle. But if the circle has become so large that it forms a straight line, any point on the circle can get to any other point by moving only through the 1st dimension. Let's consider a square that is bounded by 2-dimensional figures. As long as the 4 figures defining a square are circles, they are 2-dimensional. Once they become straight lines, however, they are 1-dimensional. The planes defining a cube develop out of 3-dimensional figures, spheres, when 1 dimension is removed from each of the 6 spheres. These defining surfaces come about by being bent straight, through reducing their dimensions from 3 to 2. They have sacrificed a dimension. They enter the 2nd dimension by sacrificing the dimension of depth. Thus we could say that each dimension of space comes about by sacrificing the next higher dimension. If we have a 3-dimensional form with 2-dimensional boundaries, and so reduce 3-dimensional forms to 2 dimensions, you must conclude from this that if we consider 3-dimensional space, we have to think of each direction as the flattened version of an infinite circle. Then if we move in one direction, we would ultimately return to the same point from the opposite direction. Thus each ordinary dimension of space has come about through the loss of the next higher dimension. A triaxial system is inherent in our 3-dimensional space. Each of its 3 perpendicular axes has sacrificed the next dimension to become straight. In this way we achieve 3-dimensional space by straightening each of its 3 axial directions. Reversing the process, each element of space also could be curved again, resulting in this train of thought. When you curve a 1-dimensional figure, the resulting figure is 2-dimensional. A curved 2-dimensional figure becomes 3-dimensional. And finally, curving a 3-dimensional figure produces a 4-dimensional figure. Thus, 4-dimensional space can be imagined as curved 3-dimensional space. At this point, we can make the transition from the dead to the living. In this bending, you can find spatial figures that reveal this transition from death to life. At the transition to 3-dimensionality, we find a special instance of 4-dimensional space. It has become flat. To human consciousness, death is nothing more than bending 3 dimensions into 4 dimensions. With regard to the physical body taken by itself, the opposite is true. Death is the flattening of 4 dimensions into 3.